program to invite the young scientists from worldwide. So our slogan is use tax, connect world and universe. Let's use scientists to shaping the future. So this is Alice from Peking University. Warm greeting from Beijing. So I mean, yeah, I've been here many years. Looks like forever. So yeah, I'm trying to get everyone to be happy with this program. So today, let me first introduce our speakers today. So we have Wang Peng from University of Warwick, was from UK. We have He Qian, was from National University of Singapore. And we have Honggang Liao, was from Xiamen University. So we also have a wonderful panelist, Xuefeng Wang. I haven't met her, since last year, I think once here. So today our topic is the advancing in the electron microscopy. So all these young scientists has done wonderful works in this field. So first, let me introduce, Wang Peng. So actually, I see Peng has a very special experience. So Peng has, oversee education, experience, and then back to China. I think you work in China for about 10 years, right? Yeah, in mainland China about 10 years, and then you move back to UK. So yeah, she is very famous in this field for doing a lot of interesting works here. So Peng, I couldn't wait to hear more about your story. So please share your slides, please. Stage is yours.
Thank you. Can you see me? Can you see my screen?
Yes, very good. Please.
All right. Okay. Thank you for your invitation. It's really my pleasure to be here to present recent work done by in our group. And today I would like to talk about electron microscopy, an emerging imaging technology for physical and biological science. Okay, so in electron microscopy, we always would like to achieve ultimate resolution, try to improve the resolution towards to picometer. As you can see that at acceleration voltage of 300, the wavelength is 2 picometer, whereas the resolution we can achieve experimentally was 50 picometer, which is 25 times of the wavelength. So the ratio of experimental resolution limit to resolution is too high, and so we need to continue to improve the ultimate resolution down to wavelength limit. So conventional, as 20 years ago, the resolution, the microscope we have was like aberration non-corrected microscope, as you can see here. So the electron beam diameter is about 2 angstrom. Therefore, the resolution is limited to like 0.2 angstrom. So when the aberration character trait, when the aberration character was introduced like 20 years ago, and then the resolution goes up all the way to 0.7 nanometer, and then at that time you're able to distinguish dumbbell in the silicon crystal. However, as you can see that in the past 20 years, in order to increase the resolution, we actually try to improve the hardware side. And the question is, with the current algorithm development and also computer science, can we increase the resolution by using computing algorithm, even without the good electron optics? So what we do, we try to actually get rid of the aberration character, and then using this so-called lens imaging optics, as you can see here. Rather than you use aberration character, now we take it out and then using a CCD to take entire diffraction pattern and to form this imaging method. And then we call that a lensless imaging or coherent diffractive imaging mode. And the coherent diffractive imaging CDI is not new. Actually has been implemented widely in X-ray, as you can see here. So you shine a beam on the sample, and then use a CCD to detect a diffraction pattern, and then you use computer to reconstruct the object. And in this method, people use a single diffraction data to reconstruct the object. However, there is no free lunch because the detector only detects the intensity of the diffraction pattern and then ignore the phase. Therefore, this is become a classic phase problem. You cannot directly reconstruct your object from the single diffraction data. So people try to do is people using computer to iterate between the real domain and the Fourier domain, and then with a certain constraint. So therefore we need a prior knowledge in order to achieve a unique solution of this iteration of this algorithm. The people will consider the object has a finite size, for example, a particle. However, because you have to have this prior knowledge, therefore this method cannot be applied to laterally extend the object. Therefore, it's limited this method application of this method. And then later on, there is a method so-called tychography. Now people use this tychography plus this iterative phase retrieval method, which originally proposed by Hope. And rather than take a single diffraction pattern, now we record a multiple diffraction pattern with many overlapping positions of the probe and also the sample. And this method actually works well with any instant radiations, for example, X-ray, laser, even terahertz radiations. And the resolution is theoretically limited by wavelengths of the radiation that you use. So this is the one of the setup that you can use. For example, you have a non-aberration corrected lens and form a beam and with a certain probe size. And you can shift your probe on the sample, and then you take diffraction pattern at Fourier domain. Because as you can see that this configuration is very similar to what we use in the scanning transmission electron microscopy mode, STEM mode. Therefore, in this talk, basically we will focus on this optical configuration. Okay, so now this is a scanning. This is converging beam, and rather than we focus the beam on the sample, now we are using highly defocused beam, as you can see that and then we scan the beam along the sample in XY direction. At each position, we take a diffraction pattern like this one, and then because we scanning our probe on the sample, at each position we have a diffraction pattern, and then we can form this 4-dimensional data, and then we feed this data into the computer algorithm. Hopefully, we can reconstruct object that we have. And this is a simplest flowchart of the iteration that we use. Firstly, we have a guess function of the object, and we use probe function multiply this guess function of the object, and then Fourier transform to the Fourier domain, which is diffraction pattern. And then because we acquire the diffraction pattern in density of the diffraction pattern, therefore we can replace the modulars of the calculated diffraction pattern and then keep the phase. And then we inverse Fourier transform and to update object function at this probe position. And then we can continue to next probe position and then so on and so forth. And this method has been very successful in terms of resolution. As you can see here, people already achieve super resolution and then still holding the world record resolution in the electron microscopy here. And also this method has been also widely used in the X-ray, such as diamond light source in all over the world, in synchrotron in all over the world. Okay, come back to what we would like to apply this method to. Okay, the challenge actually in the cryo microscope biological imaging. So in the biological imaging, people using single particle analysis or two tomography to reconstruct three-dimensional structure of the biological object. And both this method actually using HRTM, but not STEM. When you use based on TM, you have some challenges. Still, you have suffered some challenges and difficulties because the biological sample are very radiation sensitive. Therefore, the image normally you have to take at lower count, lower dose. Therefore, the image suffer low signals ratio and lower contrast. In order to boost the higher contrast, you have to increase the defocus. For for example, like here, if you want to see this virus particle. But as soon as you increase the defocus from the contrast transfer function, as you can see here, with the higher defocus showing in red curve, you can see a lot of you can see the oscillation in the lower frequency, which means you scramble up the information transfer at lower frequency and the high frequency as well. So which means you suffer the information transfer, and then it's very hard to have a very high resolution at higher frequency. Okay, at higher frequency. So that's what happened to the TM. But however, people are not always using STEM. The reason because in the STEM, normally we use STEM hard diff to achieve high resolution. If you use hard diff detector, as you can see, this is hard diff detector geometry, where you can see that in the hard diff detector, which you only detect high-angle scattered electrons, which means you have a lot of electrons actually missed by this detector. Okay, although you can achieve really high resolution, but you miss a lot of electrons. Okay, so what we do is maybe what we can do is in terms of pyrography or CDI, which we use a two-dimensional pixelated detector. Okay, we detect all the electrons in the diffraction domain, and they use use all the electrons to form the image. Maybe we can achieve much better dose efficiency compared to conventional STEM. Okay, so now let's have a look, compare with conventional STEM in focus mode. As you can see that with electron dose at 2000 electron per angstrom square on this molybdenum disulfide sample. So you barely see the molybdenum disulfide crystal information. However, if you use pyrography, okay, you can see much better atomic column. If you draw a lump profile across the atomic column in the STEM mode, as you can see that it's very hard. As you can see that this is the black curve is a signal, and then the right curve is the noise. So the signal and noise ratio is in the STEM hard diff is about 1:1. However, when you look at the typography, and the black curve is a signal of the atomic column, and the right one is noise. So the signal noise ratio is about 30. So which means using typography reconstruction method, you heavily increase the signal noise ratio. That's because you record entire diffraction pattern, all the electrons actually has been used for the imaging. Therefore, therefore tychography has very high dose efficiency and signal noise ratio. And then it's going to be very suitable for low dose imaging, especially for the soft material such as biological sample. So, and Tycho is not only has a high dose efficiency, but also very sensitive to the light atom, as you can see here. Okay, so this is lab 6, and lanthanum has a 57 atomic number. Boron is 5. In hard diff, you won't see any boron atomic column in the image. However, in the tychography, you start to see the boron atoms in this heavy crystal materials. Not only that, but also we're able to see very high contrast of the organic material surrounding this inorganic material. For example, this DNA, as you can see in the TEM mode, the DNA, it cannot be seen, together with the gold particle. But if you change it to the tychography, the DNA strand can be clearly observed altogether with the gold balls. So as you can see, the Tycho has this 3 type of merit or advantage, and therefore it will be really good for biological imaging. And this one is our first implementation in the cryo biological imaging using electron tychography. As you can see here, so we prepared the sample in standard cryo method, and then this sample is it's a vitrified viral particle, and then we kept this sample in the cryo holder at a liquid nitrogen temperature. Rather than using TEM mode, now we are using diffraction mode using this pixelated detector, and then we able to reconstruct this high contrast information of this viral particles. This is TEM. This is conventional electron dose, as you can see here. And if we change to tychography phase imaging, now the contrast of the viral particles are very strong compared to conventional TEM. And then if you look at Fourier transform of this image, as you can see that the reason why we're able to see the strong contrast because of the low frequency within this Fourier transform, okay, compared to the TEM mode. So now if you want to understand why Tycho has a better contrast, so we need to look at this so-called contrast transfer function. Okay, so this is the bottom one is a TEM contrast function with a different defocus. As you can, with larger defocus, we push the contrast function to lower frequency. However, at higher frequency, we are scrambled the information. But as you can see, in the Tycho contrast function, so the transfer function actually all above the 0. There is no intersect or crossover like TEM, which means the Tycho phase imaging does not suffer the contrast reversal. Okay, this is the first take-home point. And secondly, and we able to change the bandwidth of the information transfer by changing the converging angle. As you can see here, with the larger converging angle, we're able to achieve much wider, much higher information frequency transfer. Okay, this is second. And also, well, we have really wide information transfer bandwidth. Okay. So because we have such good contrast, which means we're able to continue decrease the dose from the 20 electron angstrom square to 5 electron angstrom square. And then we demonstrate using both type of homogeneous particle and also heterogeneous particle like HIV. And then we're able to scan much larger field of view because of the biological sample not normally have a larger size. Okay, so because we're able to have such good contrast, therefore we're able to pick the particle out, and then we can fit those particles into so-called single particle analysis, three-dimensional reconstruction. So this is, as you can see, we're feeding to with 1 million radian, 3 millimeter, and 4 million radian. Therefore, we're able to achieve much higher resolution when we increase the converging angle. So now we can compare with the TM, and then we able to reconstruct similar TM 3D reconstruction with aberration, non-aberration corrected TM type single particle analysis reconstruction. Okay, so with continue increase the converging angle, we should be able to achieve atomic resolution. For example, this is a simulation we show with 15 million radian converging angle, we should able to achieve 0.2 nanometer resolution in three-dimensional reconstruction. Okay, we also propose this this acquisition and the reconstruction protocol, so where you can able to you can combine the tychography with current state-of-art 3D single particle analysis and to reconstruct high resolution TM high resolution 3D image of the particle. So future perspective, so we think, oh, there will be we combine with tycho and the single particle analysis, we probably will aiming for a much smaller proteins, which is the difficulty of current difficulty of cryo-EM analysis. So apart from the single particle analysis, we also can combine with tube tomography and optical section. This is a tube tomography. We take each image at each tube angle of the sample. We can reconstruct three-dimensional imaging. We also can take advantage of the narrow of the depth of the focus, and we scan the sample at the different depths. We also can achieve three-dimensional reconstruction, which we call optical sectioning. For tychography, so you also can combine these two techniques by combine with tube tomography, and then we will be able to achieve this three-dimensional reconstruction of the DNA and the gold particle. And we also can combine with this so-called optical section tackle with the three-dimensional optical sectioning. In this case, we divide the sample mathematically in three-dimensional using multiple slices to represent 3D structure of the sample, and then we able to reconstruct three-dimensional structure of the object. Okay, so now with for the next 7 minutes, I would like to talk a little about for STEM for the material science. As you know, the aberration corrected STEM is very useful for the material science because you're able to simultaneously acquire high-def atomic resolution high-def imaging and also atomic resolution chemical mapping using EDX and use. But using conventional tychography, we have such problem now because we use pixelated detector to collect all the electrons in the diffraction pattern. So the CCD actually block all the electrons to enter this EU spectrometer, which means we cannot combine with this tychography together with the use mapping. Now we come up a new method. So we will say, can we combine tychography together with use using this hollow type of detector? Okay, so that we can combine this tychography imaging together with this use mapping. Now the question is, can we still reconstruct the tychography phase imaging using this hollow type of detector? So now we design this type of imaging system. Okay, we using this pixelated hollow type of detector. Okay, combined with a stem, and then so that we can allow some of the electron passing through this hollow detector goes into the EOS spectrometer. Therefore, we can combine with tychography, reconstruction, and the use mapping altogether. So the question is, can we reconstruct the 4D data set phase using this limited data set, okay, on the hollow detector? The answer is yes, we can. As you can see here, with this hollow 5 milliradian hollow angle, we able to still reconstruct the face of the molybdenum crystal. Compare with the whole detector, so the resolution we almost maintain the resolution of the image using this hollow type of detector, which means with this method, with this mode, we not only can achieve the phase of the tychography phase imaging, but also we also can integrate high-angle scattered electrons to achieve conventional hard-diff image, and also we can achieve this DPC, differential phase contrast imaging as well. And with all those 4D STEM imaging, we're able to combine with use mapping and EDX. So this is a really truly a multi-channel, multi-dimensional STEM system for the future characterization. All right. Okay. So I think what we would like to say that with ultra-fast detector, we able to scan the beam along the sample to form this four-dimensional data set. And rather than use physical optics, now we are using this so-called digital lenses, using computer algorithm to form an image to extract information of the sample. Okay, and in this talk, I have to tell you about we able to do light atom detection. We also can do low dose imaging, and then we able to combine with the use and together with optical sectioning and also two tomography, and we able to carry out three-dimensional reconstruction. We first time apply this method to cryobiological imaging. Okay, and furthermore, we combine with state-of-art single particle analysis to achieve this first time a combination of the tychography phase imaging together with single particle analysis. Okay, so I think it's really exciting time for this 4D imaging. So I would like to use final time to acknowledge the people have been working with us and our group members, and in the Nanjing University and also in Warwick, and also the people from the electron microscopy field like Angus Group from the Rosalind Franklin Institute, and also Diamond Light Source, and the people from the University of Oxford, and also Science Tech. And also people have been providing the biological sample like Pei Jun Zhang from EBIC Diamond, and Andrew David Stute from Oxford Structural Biology, and also Jingdong Song from Chinese CDC, and Professor from the Jiaotong University, and also the founding agency as well. And in the end, I would like to thank everybody here to listen my talk. Thank you very much.
Okay, wonderful, Peng. Yeah, so nice work, exciting. It's 4D, not only 3D, 4D, 5D. So yeah, you really have a magic too. Yeah, I love this very much. So yeah, yeah, as a programmer, we are moving on for next speaker. Then we back to the discussion in the end. Okay, yeah. Yeah. Let me introduce the next speaker. Our next speaker is from Singapore National University of Singapore, He Qian. He Qian also has a very qualified experience. He got, BS and master in Tsinghua University, then go to US. I think it's about 10 years, right? Yeah, 8 or 9 years to PhD and the postdoc, and also in the academic, and then he go to UK. So some kind of experience for 3 years, yeah, in UK, then go back to Asia. I think now he has a lot of story to share with his wonderful work in the microscopy for the better catalyzing. Yeah. So, Chen, please.
Thank you, Prof. Zhang, for your kind introduction. Thanks, Prof. Wang, for excellent talk. I learned a lot. So now we change gear a little bit. We talk a little bit about application of electron microscopy. So hello, everyone. My name is He Qian from National University of Singapore. Today, it's a great pleasure to attend this online seminar series. Thanks for the invitation. So today I'll talk about some applications we have been doing using electron microscopy to study catalysts. And today we're going to specifically focus on electrocatalysts. So this work is funded by National Research Foundation of Singapore, Ministry of Education, A*STAR. So thank you very much. Okay, so next slide. Okay, so I'm a microscopist, but I'm particularly interested in study catalyst. There are several reasons for that. One is that catalyst is such an important subject, right? So it's a it's a hidden hero, unsung hero in our modern lives. It's plays fundamental roles in keeping the food safety, making the fertilizers to keep make sure that we have enough food and all raw materials, plastics, fibers, and as well as keep the environment clean, like exhaust catalyst. It has a huge market, so that means that if you can make a small improvement in catalyst, usually it can lead to a big impact. Perhaps more importantly, catalysts, many of the key chemical reactions that needs to be developed to achieve a sustainable future require us to develop better or even new catalyst. Such as examples include people working on green chemistry, try to make the product with less waste, also try to utilize a vast amount of biomass, as well as the hydrogen economy. But on the fundamental level, the catalysis process happens, especially the heterogeneous catalysis, happens on the surface. If you have some molecules that you want to transfer to your product, usually what happens is that those molecules will interact with your catalyst first at the atomic level. Then it will have a different reaction pathways lead to different products. This is basically what we want to achieve in catalysis. Obviously, this is a very complex process, and is a truly interdisciplinary field, right? It requires chemical engineering, surface science, new materials, new chemistry, spectroscopy, modeling. So as microscopists, we're really working on on the material side, right? We try to understand what this catalyst look like at the atomic level, and try to figure out why they work and how to better make them, right? So if you identify a particular structure that is good for catalysis, you want to be able to make a lot of them to make a practical catalyst. So this is basically our task, and it's truly a collaborative work. So at NUS, we have we try to create this interdisciplinary subject within the group. So half of my group works on microscopy method. We mostly try to apply the method, and once in a while we also develop a new method. And half of the group working on creating new catalyst and try to take advantage of the atomic insights that we can obtain from the microscope. So for the past few decades, right, microscopy technique has evolved a lot. We just heard the Prof. Wang's excellent talk, and he also mentioned about the so-called aberration-corrected scanning transmission electron microscope. So I just want to give you one of my favorite example why that is a big deal for the catalysis science. As you can see on the left-hand side, this is a gold nanoparticles supported on titanium, and this was developed in around 40 years ago by Professor Haruta from Tokyo. And so why is this a big deal? Because gold is typically considered an inert metal, right? And it doesn't really react with oxygen or hydrogen, so usually from the catalysis point of view, it's kind of useless. But then Professor Haruta discovered that if you make gold small, if you make gold nanoparticles, they can be the best catalyst for many important reactions. Okay, but at the time, right, we don't have a aberration-corrected stem. This is 40 years ago. This is a high-resolution TEM. It's the best we have got. And so that the limited capability of a microscopy really give us a limited perspective of what the material looks like. So people naturally will think nanoparticles will be responsible for all the catalytic performance, and then they will lead to further theory, a lot of experiments. And then later, around the late 2000s, when the aberration-corrected stem becomes more popular, we study the same catalyst using a different microscope. Then we found that in addition to have nanoparticles, we still have a lot of nanoparticles. There are a lot of atoms clusters that were not visible in the regular TEM, but now we can clearly see them. They exist on the support from the AC stem. It turns out those species are more active than the nanoparticles. They are predominantly responsible for the performance of this catalyst. So this is a classic example of the best of our characterization capability really determines the best of our materials knowledge. Okay, so today I just want to share two stories of our recent works. Right, so the first story is that once you have such a powerful imaging tools that allow us to assess the atomic structure of the catalyst, then you can really develop a new method to make better catalysts. So this is I would like to use this analogy, like using Lego bricks and try to build a small chemical factory, right? So basically, this is your catalyst doing the chemical reactions. This works in collaboration with Dr. Gao Qiang and Prof. Zhu Huiyuan from University of Virginia in the US. They are the chemists responsible for creating the material. Dr. Pillai and Professor Xinhong Liang from Virginia Tech. So they are the brains, the theoreticians, try to help us to understand the process. And Wenjie and Bingqing from US, they are the microscopists. They are really the eyes, allow us to see the materials and try to make sense of them. So the reaction we worked on is the ammonia, the nitrate reduction reaction to ammonia, and this reaction can sort of convert the kind of a useless nitrate into a more useful chemical ammonia. And some people say this will be a alternative route to replace the Haber-Bosch process that is consumes about 1% of all electricity, all energy nowadays to make ammonia. This reaction, to understand this reaction, theoreticians have developed a theory, right? So if you want to make a good catalyst, you want to balance the power of the catalyst to bind the nitrogen species as well as the nitrate species. The optimum value is around here. However, if you look at this plot, right, these are the single metals. So these are, and you can see that if you have a strong binding energy of nitrate, you usually have a strong binding energy of nitrogen species. This is so-called a linear scaling relationship. So So no matter what metal you use, you cannot really reach the optimum value. But the situation will be changed if you use a intermetallic catalyst. The reason is that if you have the binding energy will be affected by the second nearest neighbors, right? So this is a surface atom, then the metal underneath on the second layer will be able to affect the binding energy, so to sort of break the linear relationship. And you can see there's different combinations of intermetallics. You can see then we find out, okay, the copper zinc or the copper palladium, those are the elements that are easily accessible. So we try to in addition, other than the rhodium, which is a rare, very precious metal, very difficult to get, a very expensive metal. Copper, palladium, copper, zinc are relatively easy to access. So we try to make the copper palladium catalyst. So that is what we get. So you can see we can make a intermetallic copper palladium thanks to Hui Yuan's team at the University of Virginia. And the microscopy results say indeed we have the intermetallic phase. And if we show if you do the catalytic reaction, we can get a very active, more active than the monometallic counterparts, copper and palladium. And they are also quite stable as well. So this is very good. But we have a problem, right? So yes, if you make a copper palladium catalyst, the bulk intermetallic alloy, it can outperform palladium and copper. However, since the catalyst happens on the surface, you're effectively wasting a lot of a precious metal, in this case palladium, inside the material. Okay, so it will be much nicer if we can just make just put the precious metal on the top surface, then without wasting them inside, right? So this is basically becomes the next goal of how to develop a next generation catalyst for this particular reaction. So this is what we have achieved, is that we use a simple galvanic replacement method. Okay, basically you make a copper nanoparticle first, then you put them into a solution that contains precious metal cations. Then the galvanic replacement reaction takes place. And then at a relatively low temperature, you can see that we can form an intermetallic phase only on top of a few layer surface. So that this will give you the intermetallic phase that you want to break the linear scaling relationship for the reaction. At the same time, you don't waste too much precious metal inside the material. And we can say, sorry, this word this should be palladium. And you can see that we can try with palladium. It works with platinum, and also works with gold. And it doesn't just work with cubic, right? We use cubic because it gave us a very well-defined structure so that we can do some nice imaging. But if you just use a round spherical particle, polycrystalline particle, it sort of will work as well. Sometimes you can see this intermetallic phase quite obviously. So this is very nice. Not only that, because we have this surface intermetallics, and they have this epitaxial structure, they actually have a slightly different structure than the bulk intermetallics, because they are sort of strained by the copper nanoparticle inside. And we can actually quantify this strain just by using the high resolution imaging. Then we found that there were some residual strains on top of us on the surface. The strains kind of are getting relaxed slightly, but you also always have a little bit left on the surface. And unfortunately, when we try to do the calculation, we found that this little bit of strain is actually take this absorption energy away from the optimum. So it's actually slightly worse than intermetallics that is that without a strain. Which also means if you can just make this layer a little bit thicker, then you will have less strain, then you should have a better performance. That is also exactly what we found later, which I didn't include in this slide. We also worked on the reusability of the catalyst. So this is related to the catalyst stability, right? And you can see that by 20 cycles of the reaction, it works pretty stable. It works very well. If you look at the catalyst after 20 cycles, you can see that the intermetallic layers are still on the top, even though some of the copper metals sort of get leached out from the core. That we don't exactly know what's going on, but probably there is some oxidation, and some oxidation happens, then the copper cations may get dissolved into the electrolyte, but the intermetallic still remains on the surface. So this leads us to this stability test. Really leads me to the second topic, which is you build this factory, right? You spend a lot of time building this factory. It works very well, but if it's not stable, then you will eventually becomes bricks again. It doesn't work anymore. And this catalyst stability is actually such an important issue, and it's probably one of the most important issue if you really want to bring a catalyst to scale. Okay, but there's a recent paper in ASIC catalysis saying that the stability of the catalyst really deserve more attention than it currently gets. Only 8% of the papers sort of study the stability. So this work is in a collaboration with a few colleagues of mine. Professor Piero Canepa, as he's a colleague at NUS, but he now moved to University of Houston, and his postdoc, Dr. Li Yuheng, they are the theoreticians. Professor Wang Lei and Wang Di is his student, so they helped us to do some CO2 CO2 reduction tests that we're going to talk about later. Dr. Xi Shibo is a beamline scientist, try to help us to get some X-ray absorption spectroscopy result, and Liu Shikai, who just got his PhD degree, did most of the work for the top story I'm going to share. Okay, so this story is about copper catalyst, right? We just saw copper, palladium, and the copper core shell particles, and this is just the copper. And the copper is a special catalyst for CO2 reduction reaction. And this reaction is important. Currently have a lot of attention because of the sustainability challenge, right? People try to take the CO2 and convert it into something useful. And copper is in it's a very unique position. It doesn't bind the CO too strongly, and it also doesn't bind so that you have you will produce CO, right? So copper is the only catalyst that can produce multiple carbon products like C2, C3 products in significant amount. So that's really attract a lot of research attention. If you read CO2 RR papers these days, it's always copper. Okay, then the stability of copper has to draw a lot of attention, right? There are a lot of studies, right? People have noticed that copper catalyst will reconstruct under the reaction conditions. So this is an STM study. Right? This is you have a nice surface in the beginning, then once after the reaction for a little while, the catalyst surface looks like this. People also study using the in situ TEM process, which we're probably going to hear more in the next talk. People find that if you have a particle in the beginning, then the particle will sort of disintegrated. But the cause of this behavior and the result of this behavior, then you'll find that there is no coherent view in the literature. In some papers, it says this process is really deactivating the catalyst. All right, so you have the nanoparticles very nicely made nanocubes in the beginning, then you have this a big mass after 12 hours reaction. In other papers, it shows that claims that this sort of a reconstruction activating the catalyst. Okay, so these two views are sort of obviously cannot be correct at the same time. So there are several hypotheses exist, right? Why this happens. There are several ones that can be easily screened out, right? Including the impurities in the electrolyte, the strain, the dissolution of the surface. Those usually can be carefully. If you do the experiment carefully, you can exclude them. But the other two are kind of more difficult, right? One is a CO induced, because there was people saying the CO will create some mobile species of the copper, and cause this this sort of a disintegration of the molecule. The other is the HER-induced, the hydrogen evolution reaction. The hydrogen is responsible for it, and both are involved in the CO2 reduction reaction. So, kind of difficult to either control them or get rid of them. And the reason that there's no sort of a consensus of what happened is that the catalyst structure is usually very complex, right? For microscopists, we look at the small part of the sample. It's kind of difficult to correlate those observations with the behavior of the bulk catalyst. So to mitigate that, we use the strategy of making a well-controlled catalyst as a starting point. Try to follow what's going on with the catalyst morphology change. So this is some nanocubes, and we found that it's very easy to get oxidized. So you always have a very thin layer of oxide on the top, a few nanometer, 2 to 3 nanometer. Then if you follow the CO2R reaction, and that process sort of follow the reported trend, right? You have the particle, then you don't have it anymore, and the performance of the catalyst does change with time. So this is consistent. Then just to try to avoid the observation bias, we try to follow the same particle before and after the reaction. And so we instead of using in situ TEM, liquid cell TEM, which is kind of a limit to your resolution because of the liquid, we use this identical location setup where we put the catalyst onto the electrode and we look at before and after the reaction. And this is basically Shikai's invention, that he has to modify the setup to allow the CO2 reduction reaction to take place. And the findings are very interesting. Is that no matter where we look, after the reaction, we always find that there is a significant morphology change of the cube. These are the same cube before and after reaction, same cube. And if you look at the outlines, right, the depths of their morphology change always go beyond the thickness of the oxide. Okay, always go beyond. And if you switch, if you have CO2R happening, it happens like that. If you get rid of a CO2, and so at this condition, there's no CO2R because there's no CO2, only HER, you also behave similarly. And only if you get rid of this negative potential, even at 0 volt, right, this potential is still enough to reduce the surface oxide. So you will see a much less morphology change, and this thickness is usually within the thickness of the oxide. So this tells us there was something else happening, other than the oxide reduction, causing this change. And also we get rid of if we get rid of the CO2, it also happens as well. So we try to do additional control experiment. In this case, we use CV instead of using, in addition to the TEM, because CV sort of samples the entirety of the catalyst, while the microscopy only look at a small part. So this, by using the two complement each other, give us a more confidence in our conclusion. And you can see here, the copper cubes give very nice signals at certain potentials, representing the 1,0 OH groups on the 1,0 surface, or OH groups on the defect size. And you can see that if you just do a 20 minutes reaction within the electrolyte at the -1 volts with potassium cation in the electrolyte, that serves our baseline. So we assume that within 20 minutes, the surface oxide will be removed entirely. Then if you extend the reaction to 65 minutes, which means any additional change that we observe will not be related to the oxide reduction, right? It will be something else. And we did observe a very significant change. See the red curve and the black curve, so it's very different. And so this is consistent with our microscopy observation. But if you remove the alkali cation, if you remove the potassium cation, if you replace that with the protons, okay, then if you repeat the experiment with 20 minutes and 65 minutes, as shown in the green and the red curve here, they are much less different, right? They are kind of similar, slight difference, but nothing like if you just put a potassium cation back, you will see a huge change again. Okay, so this kind of tells us that the HER the hydrogen revolution reaction, where it's certainly happening, where you have a lot of protons in the electrolyte, cannot be solely responsible as well. Seems like the alkali cations plays a role. So that reminds us of a classic electrochemical phenomenon called cathodic corrosion. Okay, so this is a sort of a counterintuitive process. Usually, we said, if you are studying materials, if you're studying corrosion, usually you apply cathodic potentials, cathodic conditions to fight against corrosion, cathodic protection against corrosion. But in this case, if the condition is right, if you have alkali cation metals in the electrolyte at deep cathodic conditions, deep enough cathodic conditions, you will actually trigger a new mechanism to cause copper to reconstruct. And this is what we think is happening, and no one has found this before to the best of our knowledge. So we try to understand it, and we follow the same the only cathodic corrosion theory paper out there, because this is on other metals it has been reported but still poorly understood. We use the same method following their work, and we got a similar result. Basically there is a sort of a intermediate hydride species happening that is very unstable, right? You cause the metal to leave the surface, but immediately will get oxidized and then deposit back. This is exactly what we observed in the TEM, that we have the morphology change and the deposition of small particles. We also did some control experiment, right? If we one of the characteristics of the cathodic corrosion is that if you have to have first, you have to have alkaline cation metals. Secondly, you have to have negative enough potential. So in this case, if we control the potential to be only negative 0.36 volt instead of a minus 1 volt, then we see the much less change in the CV as well as in the TEM, even though we deliberately prolong the reaction to 150 minutes. And if we only apply 3 minutes reaction at minus 1 volt, you will see the big change again, as shown in this purple curve. And notice that these two process 150 minutes at the negative 0.36 volt, the total charge transfer is the same. So it's not because in one condition the reaction goes further than the other. The total charge transfer is actually the same. So it's actually a different process going on. So in that case, if this is we believe that we've discovered this cathodic corrosion of copper, which means in your typical CO2 reduction condition, which typically happens at minus 1 volt in the potassium-containing electrolyte, you will always the catalyst surface will always change. That means if you try to create a cube which give you more 100 surface, or if you compare with a spherical particle which give you all kinds of different facets, the selectivity advantage that you have in this case to the acetylene in the beginning will not last. This is exactly what we found, right? If you after 10 hours, the acetylene selectivity changes from 33% to 25%. While if you have a spherical particle, you don't have much acetylene in the beginning, but after 10 hours, the sort of morphology becomes similar, then the selectivity becomes similar. On the other hand, if you can work with more positive potentials, in this case, negative, less than, more positive than negative 0.4 volts, you can maintain the morphology. You can actually maintain the morphology-induced selectivity. Unfortunately, for the CO2R, as such a positive potential, it doesn't make too much useful product. So we turn into the COR, carbon monoxide reduction reaction, and that's also exactly what we found. You can after for 10 hours, those are the liquid products. Then you can see that they will have a very distinctive selectivity profile, and those trends are relatively stable compared to the CO2R case. So we believe that our finding is true, and because of those experiments. The last question we want to ask us is, okay, why in literature, people still sort of report stable selectivity trend Okay, after maybe they do the experiment for several hundred hours, the performance is the same. If the catalyst surface is always dynamic, why you still see a stable performance? So we use try to use a simple model to demonstrate this idea. Basically, if you have this cathodic corrosion process, you basically you have a copper atom randomly leaving the surface and rejoining the surface. Okay, so this basically we can model it, and what will happen is that it makes the most of the difference if you have an ordered surface in the beginning. Then this will cause the biggest change. But if you have a complex structure, structured catalyst, then this atomic level sort of corrosion and redeposition process doesn't make a difference anymore, because it just feels like that, and your surface side always relatively stable. So this is basically our current understanding of why try to understand all the literature data using our theory. Okay, to summarize, I told two stories today. One is that with microscopy, we'll be able to develop novel catalyst synthesis method, try to control the catalyst at the atomic level, give us better performance. On the other hand, we also look great detail into how the catalyst deactivates. And those deactivation mechanisms sometimes can tell us a lot about the catalytic performance. And for more details, those are the references, and this deactivation work was just accepted in Nature Communications. And also, we are hiring, if you like this kind of research combining microscopy and catalysis, welcome to contact us. With that, thank you very much for your attention.
Yes, I'm answering the call. Yeah, so exciting talk and exciting opening. So yeah. Hey, yeah, well, promote that I can ask for you. So, very interesting talk. Actually, I see, dynamic on the surface and, stable. Normally, from outside, you look at that, it's quite stable for this. You go to the details, discover all this, how nice it is. So let's leave the question to the panel discussion part. Let's move to our third speaker. So actually, it's Honggang Liao, was from Xiamen University. So Honggang, I met you since last month, right, online. So yeah, I heard his talk, so exciting. So yeah, that's why today we have this super, microscopy, topic. We hope to, listen to the talks for all this, study on the surface and the study on the, intersurface, how to deal with all this, kind of special, situations. And Honggang was expert in this, has, more than 10 years, I think, or maybe 15 years was stick with this topic, and win a lot of honors. That's one of the honor I want to mention here is last year Honggang won the top 10 scientific advances in China. So that's a super honor. I think you solve a very important problem on the batteries. So Honggang, yeah, please tell us your story. Yeah.
Okay, I'll share my screen first.
Yes, please.
Okay, thank you, Professor
Yes.
Zhang, for the introduction. And I want to talk a little bit more about actually, I add two words, like the in situ in front of the liquid phase TEM. Like previous two talks, that's very nice talk. One is about the TEM and another is about the application, like in the materials and the electrocatalysis. But for me, like my talk, I feel is more like in between of them. Like we're not belongs to the electron microscopy field and also not belongs to the material science field, because when I was in Berkeley, then previous we are in the material science division, but for my group, like all of us, they think that we stay in the material science division, but they think we're not belongs to them. And we also, most time we work in the electron microscopy center, but they also thinks we're not belongs to them. So for us, for many years, like for the in situ TM field, most people think we are like some interdisciplinary things. For us, I think that's we go through a long, hard time. But for recent years, most people, they think that's very important for the in situ part. We can do more things right now. But why the TM? Why we are doing the in situ? Why we do the sample in liquid environment? I think the most important thing is the most reactions, like the daily reactions that's in the liquid. But since 1930s, the first TM developed. The TM right now is very important. That's very useful to us that can do the atomic resolution imaging. So that's a lot of things we can see right now by TM. But there's still some limitations for TM because for the gas and liquid samples, because of the scattering of the molecules, the gas molecules or liquid molecules, the scattering that's very strong. So the electrons have very short mean-free path in gas and liquid. So like the previous design of the microscope, or like the original design of the microscope, the figure here, that's the original one. The TM, actually that's a metal column inside the column that should be to a high vacuum, because all these samples should be in high vacuum. So also previously, for more than 80 years, people mainly working on the solid particles. So, but for us, we want to do something different. We want to see the samples in liquid. The good thing is with the development of the MEMS techniques right now, with the fabricated liquid seal, we can sandwich liquid in between, this kind of silicon nitride membrane. And right now, after we have an ultra thin silicon nitride membrane and sandwich a nanometer size liquid film inside. The electron beam can go through the liquid, and we also can get the image inside the particles image inside the liquid. Next for here, this is a liquid seal designed by Jaime, my previous advisor in Berkeley. And in this design, there's two chips sandwich the liquid as I mentioned. One is the top chip and one is bottom chip. On both top and bottom chips, that's based on that's a silicon frame. On the silicon frame, this ultra thin silicon nitride. Normally the silicon nitride film should be 25 nanometers, and at that time. Right now, we can go to 10 nanometers right now. So with this kind of thin membrane sandwich liquid, we can do more things, and we can image simple in liquid. But for this idea, how to do the liquid sample, it's very simple. As mentioned, we just sandwich the liquid inside in between two membranes. In the early 1930s, people is trying to use two metal thin film to sandwich liquid in between. But at that time, the resolution that's very bad. That's almost I remember that's about 1 micrometer resolution. And until 2003, Frances Ross, right now she's in MIT, and she developed this kind of modern liquid seal that's silicon nitride based. At that time, she used this kind of design. It can reach a 5 nanometer resolution. Later, Jaime developed a new design of liquid seal and get the resolution to 1 nanometers. At the same time, in 2010, Professor Chongming Wang developed this kind of open cell TEM. Right now, with that kind of design, we can do some charges of battery materials. And in 2012, in Palo Alto's group, they developed this so-called graphene seal. This kind of graphene seal, that's that's pretty easy to sandwich liquid in between, and we can do more simple things. Here is some early applications of liquid seal TEM. And early stage, people are mainly work on the liquid seal. They are more, I think that's more about the crystal growth. For Jaime's paper, and later there's more than 10 papers. These early stages, they are more about the crystal growth. No matter Frances Ross' Nature Materials paper, that's a copper deposition, and later Jaime's paper, that's a platinum crystal growth, and later in 2012, after I went to the Jaime's group, we work on the nanowire growth and the shape evolution of nanocrystals, and also the graphene seals. That's also about the crystal growth and also crystal etching. So, and the early development, I think that's I want to talk a little bit more about that. In the early times, that's really difficult for us to achieve the imaging of liquid samples. When I was in Berkeley, and the first time, Jaime told me that in 1 month, if you can see the particles in liquid, that would be great. But after I work on, I think that's about 2 weeks, I work on this kind of like how to assemble the liquid cells and make the put the cells onto the holder and into the TM. After 2 weeks, I try to get actually I think I get an image of the particles in liquid, but at that time, that's very difficult to sell the cells. So we can only image in samples in liquid for a few minutes. I feel that's quite difficult. And then later, because I was graduate from chemistry department, so I'm trying to do something different. I try to use epoxy to seal this kind of nano channels inside the liquid cell. I use this kind of, I think, slightly change this sealing techniques we achieved like for weeks. We can put the cell very well, and then we can put the cell in high vacuum for weeks. And even in weeks, the liquid could be stable, stay in the liquid cell. Because of that, then later we can do a lot of things. That's early stages and early time when we're doing the liquid stuff. But later, after I back and to be an independent professor and in Xiamen University, people ask me, what are you going to do next step? So I'm also thinking about maybe we can do something more. We can, because I feel that like the TM, that's a microscope. Microscope, that's a universal tool. So we can see anything you want. We just enlarge the samples. So if we, based on the liquid cells, like the MEMS fabrication techniques, we can do more things. We add the heating and biasing and also light source and nano indentation stuff. We can right now we can do for sensing. So based on this kind of techniques, we can do more things. But that's not easy for me. That takes me about more than 4 to 6 years. It's 5 to 6 years should be. And 5 to 6 years, we just developed the liquid cells fabrications and also holders. But right now, after a few years development, we finally achieved like the atomic resolution imaging in liquid with this kind of liquid and gas flow, heating, biasing, light illumination, also for sensing. And also based on the different types of liquid cells, we can do different things right now. We have different series of holders, like the liquid holder, gas holder, and the double tilt heating holder, cryo holder, and also nano indentation holder. Here is I think I want to talk more and show how our liquid holder works. Like the most commercialized liquid holder, they show the so-called bypass technique. They put they drill 2 holes on the sidewall and the sidewall of the liquid holder and put the chips, the top chips and bottom chips inside the trench. And the liquid will flow, get out from the hole of the sidewall of the holder and will wrap the whole liquid cell. So why they call bypass? I think that means because there's a part of liquid they go through around the liquid cell, and they also have another channel inside the nano channel inside the chips. That's where we need the electron beam should go through. But in that case, the bypass, there would be a lot of liquid get into the front part of the holder. In that case, once the window of there's a nanometer size, nanometer thick silicon nitride membrane. There's a lot of liquid around the whole cell. Once a window breaks, there will be a lot of liquid get out from the liquid cell. Well, will damage the electron microscope. So I always want to find something different. So after a long time try, right now we can connect with the nanoliter flow control system. With the nanoliter flow control system, we can connect the flow channel and the nano channel inside the chip together. We direct connect all this type of channels inside, and we can get the fluid process control of the fluid inside the chips. We can make the liquid or gas go through the chips nano channel. We can flow back and through and sequentially flow the gas or liquid inside. So right now, based on this kind of direct flow, we can do a lot of things different. And also we developed softwares to control the temperature and the night radiation. So with our self-developed software, we can get the temperature heating, and here we can get the high resolution imaging and 1300 degrees C, and also we have a precise control of the 0.01 degrees C of the stability of the whole sample. Why we need so stable temperature control? Just because, if we want to do atomic resolution imaging, everything under the TM beam should be ultra stable. So for a heating sample, if their temperature the shaking or unstable, the sample will be move around. That's the reason we need the should be ultra precise control of everything. And previous, I mentioned that with the direct flow of the gas or liquid through the nanochannel, we could observe something very interesting. Like previous people working on the MEMS part, they flow liquid into the MEMS channel. They can mix the two liquid, mix pretty quick. But people don't know too much about the details and the nano or molecular level. So after we do the experiment, we use nanoparticles as a tracer for the fluid motion. So after that, we just trace the motion of the nanoparticles. We can see if we sequentially flow the gas and liquid through, we first flow the liquid and then flow gas through. There would be a bubble goes through the liquid. Because previously there's a liquid flows through the nanochannel on the nanochannel surface, that would be left a little bit of liquid on the surface. And when the bubble goes through, there would be an evaporation of liquid. The concentration will be increased a little, and just because on the surface, then that's an ultra thin liquid film. So if there's a bubble goes through on the surface, the evaporation might not be a significant evaporation, but the increase of the concentration would be a lot. So the nanometer size liquid film, just a tiny evaporation will increase a lot of the concentration. The concentration gradient on the surface will, when another liquid come to the surface, they will significantly increase the concentration gradient will drive the nanoparticles inside the liquid move. Their movement will be increased 2 orders. And with ultra thin silicon nitride membrane, we can do something we can direct and go to the atomic resolution imaging, and also both in TM and STEM mode. So based on that, we can also do something like the EDS and EOS in liquid too. Because of ultra high resolution, so we can do something in previous we cannot, like the imaging of single ions and their dynamics in liquid. Previous people are doing the imaging of polymer ions in cryo-TEM. I read the paper, but it looks like their resolution can only reach similar like this one, this figure in the center. They can only see dark spots under the TEM. But when we use our liquid cell, we can see that here. That's an image here. We can see the hollow structure of single ions. And also that confirms that single ions. And we also, sometimes we even can see the counter ions absorbed on the hollow structures. So with this kind of ultra clear images, and we demonstrate that we can image single ions in liquid, and also we can see the dynamics of them. That's a very interesting thing. That most previous we think like the ions or other nano object, we can only see that they have that kind of so-called Brownian motion or random motion inside the liquid. But we found that if we can track single ions diffusion, we found that there's a totally different motion types. We call the hopping motion, like the hopping motion over here. We can, if we trace their movement, we found that they can, like here, their move patterns, like they can move back and forth and 2 spot, or they have a certain patterns like the 3 or 4 spot, they just move back and forth and a different site. So this kind of hopping motion previously was not identified, and we could not imagine that if we don't have this kind of in situ observation. Later, I want to show something very important and recent. I feel that would be very important for electrochemistry. We have the atomic imaging of a solid-liquid interface. Based on this, we can work on more about the electric double layer and electron transfer reactions. For the electric double layer, this kind of model have been used for more than 100 years. That's a simple model. Just as I feel that's based on very simple things. That's just the charges on the metal surface, and due to the charge on the surface, they will attract the counter ions on the liquid side. And this kind of simple model, they didn't consider the size and the interactions of ions, also didn't consider the interactions between ions and the surface. Like the ions and the surface, there's the van der Waals force and also electrostatic interaction force. And there's also no high spatial resolution direct observation, so we can only assume that they follow some basic laws. But right now, I feel at this point, we would be able to do something more. We can, at a single ion scale or a single molecular scale, we could be able to see if the traditional electrical double layer models that works or not. And based on that model, we can also do more about understand more about the charge transfer reactions in electrical double layer. I like this sentence very much. That's from Albert. He's the 1933 Nobel Prize winner. He says that life is nothing but an electron looking for a place to rest. And I think that's very interesting. Is about how they talk about how electrons move around. Actually, for electrons, right now I feel the electron could be moved easily, and they can moving around everywhere. And for the electrochemistry or other chemistry reactions, the most important thing is about the charge transfer. And for the charge transfer, there's two mechanisms. One is the outer sphere electron reaction, and another one is inner sphere electron reactions. Based on Marx's theory, the electron transfer should be before or after the electron transfer, their arrangement, like around the ions, the molecules arrangement should be changed. So that could be, then the electron could be stable and stay and somewhere they can transfer. But all of that based on the electrical double layer, the simple model previous I mentioned, all of this model, they have very simple, like the counter ions on the solid, on the liquid side and the charges on the solid side. But right now, with the in situ liquid phase TEM, we can see for colloidal nanoparticles inside liquid, there's a dense liquid phase around the particle. If there's a dense liquid phase around the particle, that couldn't be exactly same as the EDL model predict. Then we do more and try to understand more about the electrical double layer. Like in this case, we use spectra and EOS to check. We found that inside the double layer, we cannot see that's a traditional electrical double layer. That's a dense phase layer around the nanoparticle. They have ions and molecules, like the outer molecules and the counter ions, and also like here that we have indium atoms inside. And based on DFT simulation, we found that because of this kind of layer, they have ultra dense ions inside this, because the distance between ions that's very close, and the electrons could be easily transferred between these atoms, and then they form some kind of loose network. In this network, they have some kind of charge-free transform between each other. I feel that's more like some kind of chemical bond. So I feel that's the reason they have a phase segregation between the bulk liquid and also the solid part. And we also could see when the dense phase formed on the nanoparticle surface, we see that during the formation of the dense phase layer, there's an H process. How we describe the H process, because if we have a statistic of the core size, we said during the formation of the outer layer, we can see that there's a charge separation, and the surface, like the surface atoms, they left charge on the box on the solid side, and these ions go to the solution side and form this kind of dense phase. And we can find that very interesting things. And in the dense phase, there's, like previously mentioned, that there's atoms inside. These atoms can aggregate and to form clusters or nanoparticles inside the dense phase. And if we see there's nanoparticles, tiny nanoparticles get into the dense phase, they also can be dissolved, which proves that previous DFT simulation, there's both ions, atoms, and also counterants and solvent inside. So previous, that's a very simple colloidal particles, and the electron double layer model might be that kind of situation. And then we apply biasing to see what's different. In this case, we found something very interesting, like we call interfacial charge transfer reactions observed in lithium sulfur batteries. So with a very simple, like just a simple electrode, like metal substrate, we can see this kind of electrochemical reaction. That's very simple, just like the thing in previous theory to predict, like the reaction of the molecules on the surface. They go through a step-by-step transformation, and the dissolution or growth then works on the surface. But later, after we modify the surface of nanomaterials, we add the metal clusters and decorate the surface of the graphene with metal atoms on the surface. We found that during the reactions, there's molecules, and polysulfide molecules could be aggregated on this active center. So on the active center, they continue to gathering the polysulfide molecules on the surface, and then form a dense phase droplet like droplet. This droplet, that's very like the previous we mentioned. The previous shows the dense phase around the nanoparticle surface. And because in this situation, we apply biasing, so that's a discharge process. During the discharge, electrons continue to get into the droplet like dense phase. In this like a bubble like dense phase, they can continue to get more and more electrons, and there's no any change at that time. Once they get enough electrons, they will suddenly change to a totally different materials. They transform to lithium to sulfur and nanoparticles. So later we use we check the product. We find that they directly form the lithium to sulfur. And the previous on the bare electrode, there's no without the active center. The surface materials, they can go through step-by-step transformation. They form the polysulfide molecules, like the lithium 2 sulfur 2 minus ions. So in this case, by the DFT simulation too, we also simulation also shows that the electrons could be freely transformed between this polysulfide and this. Also, these electrons could be stored in this kind of dense phase droplet. So which proved that, like the previous one, what could be happening inside of the dense phase. I think this kind of new phenomena and we in-depth understanding of the electrochemical reaction, also about the charge transfer on the electron surface. That's the most important things. That's a reason we could be selected as the top 10 scientific advances in China of 2023. I want to emphasize a little bit more about our findings. For the previous research about the electrochemical reaction, many about the inner sphere reaction or outer sphere reaction, but with the in situ TM, with our observation, we found that there could be some other new mechanisms. So here we so-called charge storage and collective reaction behavior. Previous are all based on single molecular reaction, but once we found that there's a lot of molecules on the surface and aggregate together, they could be like united, connect each other. Their reaction pathway could be totally different, and this could be also implies that the previous simple electron double layer model, in some cases they may not be totally right. There could be something other situations could be exist. And I also, because of limited time, I want to go quick a little bit. And we also have developed different systems like the nanomanipulation holders. We can do charge and discharge, and we can see the dissociation or deliciation of the materials. And we also work on the sodium ion batteries that could be we could directly see the ion transfer inside the materials. And we also can measure the force of during the materials compressing, and also I try to be quick. I want to say that we developed the sensors like the ultra high sensitivity sensors. Right now, we can image single particle attracting force under TEM. The sensitivity could be reached 20 nanonewton sensitivity, and we are developing a next generation of the force sensor. Or try to develop a piconewton, make their sensitivity to piconewton. And that could be more important for chemistry department, chemistry research. We can measuring like the cross-linking force between molecules and also like the van der Waals force between individual nanoparticles in the future. Okay, I want to acknowledge to Professor Sun and also Jaime and our collaborators. Thank you very much.
Okay, super, Honggang. Yeah, the nice story, as you achieved the dreaming for all the maths, researchers want to achieve for the, super high, sensitive mass detection, for the single particles or something. Yeah, so very exciting. Let's go to the panel discussion. Before that, let me introduce Professor Xuefeng Wang, our panelist. As Xuefeng was working in the CAS, Chinese Academy of Science Institute of Physics. Xuefeng was associate professor there, and he did a lot of work was on all this kind of let me see here, the interface too. Yeah, his understanding the working principle and the failure mechanism of key materials for the high energy density batteries. I think it's the right match here. So Xuefeng has many honors, published many papers. Yeah, so I will not list all of them, but highlight natural materials, ES, all these top journals. So yeah, let's welcome all our panelists and our speakers jump in for the panel discussion. I think Xuefeng already prepared the questions for all of you. Xuefeng, please.
Okay, thank you for the introduction, and thanks very much for all the talk, and very impressive for the beautiful works. And yeah, I learned a lot actually. So I also have many questions. So the first question I would like to ask Professor Wang Peng. So I'm a little confused about the two techniques, maybe called the electrical tachography, or the another name, or the another technology is the 4D scan. So is there any difference or the same techniques?
Well, okay, that's actually a very good question, as it has been yes, I think this question has been asked quite a lot. And the 4D stem, actually 4D stem, the name of 4D stem coming after the tachography, and 4D stem means you acquire, because nowadays you have ultra fast detector now. So which means you can, in the stem mode, you can move your probe on the sample, and at each probe position, you're able to acquire a 2D diffraction pattern. So because you're scanning 2D, and at each position, you also get 2D diffraction pattern, and that will form a 4D data set, 4D stem data set. Okay, I think for stem, for the definition of 4D stem, which means using this type of scanning together with ultra-fast detector, you're able to acquire 4-dimensional data set. Okay. Now the question is, with this 4D STEM dataset, how you can extract information from this 4D dataset. Okay. And tychography is one of the way to extract the information. One of the algorithm you can extract information from this 4-dimensional dataset. And also, you also have another type of technique, for example, DPC as well, right? Differential phase contrast or central of mass method, which also based on 4D STEM dataset. And then during the processing, you're able to acquire a similar atomic resolution image and so on and so forth. And also, based on 4D dataset, you also can do virtual imaging as well, right? You can integrate part of the area of the diffraction pattern, and then you can form a hard disk image, you can form a bright field image, and that's we call the virtual imaging based on 4D STEM dataset. And also, you also can do, based on 4D STEM, you do orientation mapping as well, right? Just like a EBSD, electron backscattered, like on the SEM. So you're able to form orientation of the grain, or orientation mapping of the different grains. So by doing so, you're able to, you can integrate part of diffraction spots and then to show the contrast from that spot, and that will give you orientation mapping, which also based on 4D dataset. So overall, actually, 4D STEM is talking about this type of dataset, and then tychography is more like a method or algorithm to extract information, and which originally from CDI, coherent diffraction imaging from X-ray, so yeah.
Okay, thank you very much for very detailed explanations. Yes, from your talk, I'm actually very interested in the tychography. So I'm wondering what kind of material, or is the tychography work for all kinds of materials, or is there any requirement for the materials?
Tychography basically can work with any materials, actually, really like STEM. If you use STEM to characterize any material, and actually tychography can do that as well. Give you better resolution, better contrast for the light atoms, and also very much more dose efficient, because they take all the electrons and then to form image. So basically, tychography can apply most of the, yes, as long as you can use that in the STEM, and you can use that. But the downside is you have to have a 4D STEM capability, right? You have the ultra-fast detector, and also secondly, tychography is an algorithm. So you have to familiar with computing science and in order to, make this algorithm working. So yeah.
So did you apply or try this method for the battery interface?
People actually do that. Actually, really, people use tychography to image lithium batteries, because as you know, lithium is very light atom within this transition metal. So it's very hard to see that in the hard disk image. Therefore, if you can use tycho, you're able to see where the lithium atoms are within the cathode. So potentially give a lot more information. Yeah, I think that's one of direction people people should do. Yeah, using tychography, especially combined with a in situ like a Hongang's holder, and or cryogenic stuff. Cryogenic holder as well.
I think it's
Absolutely.
for the cathode, also for the oxide, it's easy. But maybe I'm working on the battery interface, so it's
Oh, sure. Yes,
complex,
yes.
very complex. It has several kinds of the inorganic or organic materials. So I just wondered, is your method is feasible to understand the atomic structure of such complex composite or not? Yeah.
That's you set another high order to us, actual direction to us. We nobody have succeed to observe organic material, atomic resolution of organic material yet. But as we have shown using DNA as an example, as you can see that we have a DNA surrounded by no, we have a gold particle surrounded by DNA. So which means you got inorganic as a core and organic surroundings, which is forming this inorganic and organic interface. We conventional TM cannot distinguish that yet, but for us, we able to see DNA around the gold particle in 3-dimensional. But however, we haven't achieved atomic resolution yet. So if we able to do that, presumably it's going to be very useful for your purpose. You would like to see the interface between the cathode, interface, or what do you call that? Interface between the cathode and also polymers or catalysis or yeah, I think those kind of things. Yeah, I think there's still long way to go, but I think maybe one day. Yeah.
Okay.
Okay, Xuefeng.
So
Yeah. Can you give a chance to ask some questions?
Okay.
Yeah. So yeah, actually, yeah, there are many questions online. Yeah, I'm gonna choose one to ask one. For our second speaker for Chen. Yeah. So you done with the materials, as many of the students was here working on the materials. So yeah, the first work you introduce is like a factory, right? Yeah, as a right, as a calibration for the factory. So yeah, it's very exciting. Actually, I have a question is if this method can save energy as well, yeah, cost more energy or save energy. Did you think about something like in this way? Mm-hmm.
Okay. Okay, this is a complicated question to answer actually. So catalysis improves the reaction rate. It doesn't change thermodynamics. It changes the reaction kinetics. So in many cases, we can do the same reaction at lower temperature, for instance, and that could potentially save energy. And in other cases, for instance, if we are talking about hydrogen economy, right, and then you need to make hydrogen carriers, and then the energy efficiency, how efficiently you can make and transport and utilize the energy carriers becomes an issue. Then some catalysis will play an important role. I don't know whether that answers the question or not.
Yeah, I just, because I'm working in the maths area, I'm always thinking, from maybe physics side, not chemics
yeah.
side. So sometimes I always ask you do all this like energy harvest now something, for this, does you really save some energy or some question like that? That's why I ask you this. Okay, yeah. Very interesting work. So yeah, Xuefeng, back to you. Just coming in, yeah, for jumping in for question. Okay.
Okay, so yeah, in terms of chance talk, I also have a question. I not really catches the mechanism for the stabilization of also unstabilization of the copper catalyst. So what's the main reason why it is
Okay, so
I'm
the main reason we think is because of so-called custodial corrosion. Custodial corrosion is actually a known phenomenon for over 100 years. People actually using this technique has a custodial corrosion to make nanoparticles. So it is a real phenomenon. It's a sort of a counterintuitive. It has been known for a long time, but the underlying mechanism is actually not well understood. The reason is that people believe that the intermediates involved in the custodial corrosion are so short-living, and it's very difficult to catch the nature of the intermediates. So the current understanding is that there was probably some metastable hydride formed, soluble hydride formed in the process. And people there is a recent Nature Catalysis paper this year. They use the online mass spectroscopy and they try to catch that species but failed. And then they have to add a organic ligands. So the idea is by the ETH researchers, they try to use the organic ligands to catch the intermediates once it's formed. Then they manage to measure that intermediates using the mass spec. But the overall mechanism is still under debate, even though it is known, it's a known phenomenon, poorly understood.
Okay. So how fast is change, and do you think it is possible to catch by Hongang's in situ liquid TEM?
Oh, actually, the people from Fritz Haber Institute, they use liquid electron microscopy. They observe the similar phenomenon. The difficulty is that for studying copper, there were usually always oxide involved, and the oxide under custodial potential will get reduced, and some will get dissolved. So it's very difficult to decouple the oxide reduction or oxide dissolution from the custodial corrosion. That's why we think we made the discoveries, because we managed to decouple, or we managed to convince the referees that we managed to decouple the phenomenon. We can distinguish from the oxide reduction from that custodial corrosion process. So how fast you're talking about? Basically, you're talking about kinetics problem question now.
Yeah.
And the method we used is identical location, right? So we do the experiment, we take it out, we look at the microscope, or we do some CV. Also involves taking the sample, manipulating sample in the glove box. So and the referee asked the same question. And our answer is that our method doesn't really have the time resolution to give you the answer, but we know. From what our understanding is that it should happen instantly once the reaction condition is met. Once you are in a deep enough, a negative enough potential, and you have the right environment, there's nothing to stop it from happening. But then you talk about the reaction rate. We have no idea how to measure it at the moment.
Okay.
Yeah.
Okay, so does it facet dependent?
Oh yeah, it doesn't. Actually, we use the cubes that have 100 facets. The reason we use that is because first of all, it gave us a sort of a well-defined starting point, so that we can actually measure how much change has happened. Also, it gives the cubes gives you a well-defined CV curves that we can also observe the changes. But it doesn't. We also in our sample sometimes we have spherical particles. The thing happens as well. So this is also one of the questions referee asked. Yeah.
Okay.
Thank you.
Sure I'm not the referee.
You asked the right questions. Yes.
Actually, I'm thinking you are, Xuefeng,
No.
Okay. Yeah, please.
Okay, so maybe I can ask some questions to the Hong Kong. So yeah, I'm very interested in the liquid TT, special to understand or to propose the electronic double layers. So the first question is, how can we distinguish such thin layers?
You mean how can we distinguish this such thin layer surface?
So based on the composition of the contrast.
both contrast and composition. We use like the first we need to image them. We use with the contrast we can see that there's a dense phase near the surface, and then we use stem mode. We analyze them. Analysis with the stem, we can get more details about how many metal ions inside the dense phase, and also we with the yields and also other spectrum, we can see what's the chemical species, what kind of chemical species inside. And we also try to use cryo-TM. Yeah. I know you're working on cryo-TM. We are trying to use, we are trying to develop some kind of so-called in situ cryo-TM. After we see this kind of dense phase, and then we like the freeze them, and then we can try to do some detailed analysis on them. So that's a future work.
So is that so based on maybe your very preliminary result? Is there any difference between the result from the obtained from the in situ liquid TEM and the cryo TEM? Is there any difference?
Yeah, indeed, there's many difference for the in situ TM. We can see more, but for the cryo TM, that we need to the situation and also sample preparation that could be very complicated. So we still working on that, trying to figure out how to do that.
Okay. So, did you notice any interaction between the liquid and the solid in the interface? The molecule interaction.
Molecule interaction. I feel that basically we can distinguish them based on their dynamics, because the solid particles inside in the center, we can see the lattice fringes, and the surface, like the dense phase, they can quickly dissolve once the structure changes, like the particles shape and structure changes, they will quickly dissolve, and their behavior is more like liquid. And also from the stem, their concentration and contrast, they couldn't be solid part.
Okay, yeah, it seems complex and very interesting. So, and for your last work, can you explain detail on the interfacial selective reaction behavior? This is a new concept, I think.
Yeah. I think that's the most important thing of our research for that kind of a collective reaction behavior. That's so-called, why we call it collective reaction behavior, just because previously people all think like the chemical reaction, we all think from single molecular aspect. We only think about one molecule, like they get electrons and get some other, like react with other molecules. But right now we found that if there's tens or hundreds or even thousands of molecules, they are working together. They're not like previously we assumed that like the one molecule they get electrons and or get some some other atoms they could transfer to different materials. But right now, if we have 10 or hundreds of molecules, we just get 10. If we have 100 molecules and we got 10 electrons, they cannot transfer at that time. They will continue to get the electrons, like the 100 molecules get 100 electrons, and then they suddenly, all of them transfer to different materials. That's a collective reaction behavior. That's totally different from what previous the mechanism described.
So, how many molecules can work together, or the maximum molecule?
That's a good question. We try different systems right now. We could see in some system like the metals. We also see similar things during the deposition of the lithium metal. We could see that this must be 1,000 molecules together. They can suddenly change it and deposit.
Okay. So that's all my questions. Maybe I can leave some opportunity.
Yeah, I'm waiting here.
Okay.
I'm waiting here. Yeah. So Hong Kong asked, how about question for the institute liquid, electroscopy? I said, how many parameters you can control? Temperature? No, pressure? Yeah, all this can you control, the parameters for this, institute my liquid, testing or microscope. Yeah.
We try to mimic the reaction in the environment outside the TM. So we have the temperature control, the pressure control right now mainly is for a gas reaction, and the pressure of gas right now for in situ TM mainly is the maximum that's just go to 1 or 2 atm. So right now that's not very high, not very high. And but for liquid, we mainly, for example, we can add biasing and the temperature control. We also can add some like the light illumination. We can go to do some light, like the some materials under light, like the auto splitting or something else.
Mhm. Okay, that's interesting because you have a platform, right? Yeah, this was a kind of powerful platform. Then you can, adding all these kind of parameters to control to do something, to investigate. Yeah, I think that's a very interesting, platform. So yeah, we still have 5 minutes. Yeah, have a questions for 3 of you. Because I, read all your CV, I see 3 of you has qualified experience, right? Overseas and inland, especially Wang Peng, you have so interesting, the journey, right? Yeah. So study there, working there, then come back home, yeah, many years, and then go overseas again. So any kind of, experience our lessons you can share with us for the research and for the career development. Yeah, maybe Wang Peng, you can go first. You have a rich, experience. Peng, you mute. Yeah. Peng, you mute.
Oh,
Yeah.
okay. How's that now? Yeah, okay. Thank you for I think that's become yes, it's quite difficult question. I think each person have different career trajectory and also personal or family family issues. So therefore, people will choose different route. I think overall, I think no matter you working in the abroad or in China, I think you got different advantages. Also, I think as long as
okay, maybe my question is this. Okay, Paul. Yeah, so why you can transfer so smooth? What's your secret? Yeah, you transfer so smooth, right? Yeah, you be professor in China, you be professor in UK, and back and forth. Yeah, what's your secret?
Well, I think you working on something you like, and then I think if you can express yourself and in front of the different audience and then appear very enthusiastic on what you are doing and you can do it well, I think that's always helps, I think. So that's why I always, yeah, I think that's my secret, I guess. I always pass my enthusiastic to my students or to the people in front of my presentation. I think that's my advice.
Okay, maybe I can summarize like this. Once you're good, your work was good enough, right? You can transfer smoothly everywhere, right? Is that right? Yeah. So because I saw Honggang, my question for Honggang is you travel too because you published nature paper first 10 years ago in US, right? You come back and you publish another one, right? Yeah, 10 years later. So how this kind of, very exciting or outstanding works in different, environment too. Yeah. So Honggang, any kind of secret can share with us?
The different thing is like in different environment, you need to get used to the different work mode. Like in US, there's a lot of people you can collaborate, but when I back to China, I need to teach students to do things. So that takes more time. Not like previous when I was a postdoc or researchers over there, I can collaborate with professional people. Right now, I need to teach students to do things, so that will be slow. That's the reason we take another 10 years.
You mean they, delay, right? Yeah, they drag you. Well, I mean, did you get any good part for your teaching? Maybe the student can inspire you or something. Yeah. So any good part for this? For teaching?
Yeah, the student when the student learn things from you, and we as a group we can focus on the things I want to do. So for a group of people, right now we can do more complicated things. That's the reason we can develop a different system of the in situ TM stuff.
Okay, super. Yeah, I read your stories. You know that for your group, more than 10 years focus on this. Very tough questions, very complicated. Setup. So I think it really worth. To fighting for the big target, right? Yeah, take more time. To solve the big problems. Yeah. So super. Yeah. So I think maybe we many students here can, listen to that, take more time, get on the big target, right? Yeah. So, last question is about Chen. Yeah. So, Chen, you cover 3 continental, right? You cover 3 continental. Yeah. Your academic, journey covers 3 continental. So, yeah, what's you can, sharing with us, for survive in different environment. Yeah.
Okay. That's an interesting question. I never thought about it actually. I think for me, I more of a go with the flow. I think I tried my best, try to put myself in a position to do the work I like. Then really when you just have to catch the opportunities when it is presented to you. I think working in different areas, they have that I can enjoy different culture, which I appreciate and I enjoy it. So and making a lot of friends as well. So yeah, I think try your best, go with the flow.
Okay, yeah. Before you answer that question, in my mind, I'm thinking I'll say that because I'm a graduate from Tsinghua University. Okay, yeah, so yeah, the top university. Okay, that's just a joke. Yeah. So yeah, exactly right. Just follow the train and follow your heart, where you want to go. Right. Yeah. So, thank you all of you. Yeah, as a moderator, I should, always give you some surprise. Yeah, so also the questions are surprise too. Yeah. So, thank you all of you. Wonderful talks and wonderful, question and answers. So, let me, give you the certification. So, I think you have, gone through all this tough, you know, and investment, so I deliver this one to Peng. Yeah, Peng, proud of you, travel smooth and always on the top, do the best works. Yeah, congratulations. I will send a e-certification to you, okay? Because if you go Davos, we will have that hard copy for you and also a special souvenirs. So, yeah. So we prepare for all the speakers there, to deliver a hard copy and these souvenirs. So hope to see you there. And next is so He Qian, yeah. So He Qian, yeah. So proud of you. You also you wonderful talks and good experience sharing and this super materials work. Yeah. So congratulations. You all got my email too. Yeah. So next is Honggang. Yeah. So Honggang, so nice to see this top 10, science achievement, on this line. I hope, next, big breakthrough will not take such long for 10 years. Maybe less than 5 years, you will achieve another one. Okay. Honggang, yeah, looking forward to your next step. Okay. Yeah. So congratulations. And just now I say that, this year we'll have a big go together for the ICANN speakers and Davos this July 11 to 12. So we have a 2 days very high program. We'll focus on the innovation, science, technology, and also investment, management and entrepreneurs. So they will be a big go together for all the people to try to pushing innovation, science, technology forward into the new market. So we'll see many super names, bigger stars, also including the jazzy stars. So because they play music with AI, so that will be a big fun. So we try to get everyone big party and also enjoy this summer. So that's the invitation for Davos. So please come over. So go summit together. And next week, we're going to have youth talks again, and Tuesday, 8 p.m. Beijing time. So the topic will be smart manufacturing. So we got the three, speakers, also one from Nanyang Technology University, and another one was PKU, young, talent, and one from Caltech. So yeah, we have, our moderators from Duke University, and one of a young scientist in Peking University, Han Mengdi, will join too. So yeah, let's see you next week for all these wonderful talks and all these young talents shining on the stage. So yeah, youth talks. See you next week. That's the end of today. So congratulations, everyone.
先生、女士们，亲爱的朋友们，欢迎大家来参加我们的 ICANX 达沃斯科学峰会。那今年是第一次 ICANX 会组织大家一起在瑞士的达沃斯进行线下的聚会。我们有6个主要的议题。第一个是创新 innovation， 第二个是科学 science， 第三个是 technology 我们的技术，第四个是 investment 投资，第5个是 management 管理，第6个是 entrepreneurship 创业。所以它结合起来就是 It's time， 是时候了，是时候让我们去达沃斯听这些非常给我们启发的关于未来的这些报告。在达沃斯我们会有3个非常重要的论坛，一个是诺贝尔奖论坛，我们会邀请诺贝尔奖获得者来跟我们谈科学的未来，我们会邀请世界科学院的院长来跟我们谈世界科学技术发展的未来。那我们会邀请大学校长来参加我们的世界大学校长论坛，来跟我们谈关于教育的创新教育的这样的一个未来。同时呢，在达沃斯呢，我们也会邀请各行各业的这样的一个非常重要的领袖人物、领军人物来跟我们分享他们的所思所想，他们对未来的思考。那我们也会邀请非常多的各行各业的精英来跟我们分享他最精华的这样的一个思想。那当然了，达沃斯这个舞台也不只是给这些大牛们展示的舞台，也是我们来展示的这样一个舞台。所以如果你有好的故事、好的思想、好的技术、好的思考来进行分享，那也欢迎你再来线上投稿。所以我们的截止时间是4月1号，大家还有1个月的时间来准备好你的发言，希望分享给全世界的。所以欢迎你在线提供你的资料。那我们也希望你成为这个舞台上的明星。那在达沃斯呢，我们设了3个奖。第一个是针对大学生的，你是创新创业的最牛的大学生，那你来申请我们的创新奖。如果你是一个毕业10年以内，现在正在从事独立科研工作的科学家，那你来申请我们的青年科学家奖。如果你是一个创业者，你成立了你的公司还不到5年的时间，已经发展得非常好，那请你来申请我们的创业奖。所以所有的奖项申请的时间截止都是4月1号。那欢迎大家在线提供这样的一些资料，那我们也会给大家非常多的这样的机会，成为舞台上最亮的星。那是时候来我们大家一起把科学推向未来，推向世界。那这个呢是我们在达沃斯的非常重要的合作伙伴，我也希望你成为我们的合作伙伴，我们一起来推动世界的发展。那现在达沃斯论坛已经开始注册了，所以各位朋友、各位好朋友们，请你们开始尽快注册吧。我们相聚在达沃斯，我们一起 Go Summit 走向巅峰。
汽车电子化的迅猛发展正在掀起一场技术革新的浪潮。启万千期待于一身的电子元器件，必须以更高的技术水平和可靠性，为汽车电子化提供支持。多层陶瓷电容器 电感器，高可靠性元器件，太阳诱电挺身而出，肩负起推动未来科技进步的重任。电子元器件的发展与汽车、工业设备和网络时代的